desktop. Okay. Now I see the red border. So now you should see the slides.
Now we can see it properly. Yeah.
Okay, great. Okay, so so in this talk, first of all, an intro to OpenAirInterface. I want to give you a status overview of the implementation of 5G new radio in OpenAirInterface, and the roadmap ahead. And then I want to talk about, as I said in the title, about how you can use OpenAirInterface for cloud native and Open RAN deployments, which is a really hot topic in the moment. There's a lot of money actually being spent by governments on this Open RAN initiatives. And last but not least, I want to show you a little bit how we. I want to show you the Eurocom Open 5G Lab, which is one example of which is our playground for cloud native and Open RAN deployments. And of course, there will be room for conclusions and questions at the end. All right. So in a nutshell, on one slide, trying to summarize what OpenAirInterface is. So OpenAirInterface, first of all, is an open source software. Okay, that's very important. And it implements 3GPP technology. So starting at, OpenAirInterface has been existing for a very long time, even before I joined Eurocom. So I would say at least 20 years. But it really started to become popular when we started to support LTE. Okay, so that LTE, as you know, is fourth generation, and in the 3GPP terminology, this is release 8. So we started with this 3GPP release 8. Later on, we included features from LTE Advanced, also known as release 10, 11, 12, LTE Advanced Pro, release 13, 14. And now, today, we are supporting 5G. So 5G started with 3GPP release 15. 16 is now also available. So today, we don't have any release 16 features yet, but they will come. And currently, standardization is ongoing for release 17, and so forth. So we are basically following this 3GPP standard. And OpenAirInterface, so that's the first point. And the second point is that OpenAirInterface is also the most complete implementation of the 3GPP standard. So in the sense that it implements all the elements you need to actually build and operate your own network. Okay, so starting at the radio network, so which is also called the EUTRON, the radio access network, where you have the E node B, which is the base station in 4G. You have the G node B, which is the base station in 5G. You have a UE, 4G UE, and now we have the NR UE as well. But we're not stopping there. We also, so to operate the network, you need the radio access, but you also need the core network. So the core network consists of the mobile management entity, SMP gateway, HSS, home subscriber station, to manage all the network, the users and the network. So we have all of these elements. And today we also, since recently, we also have the first version of the 5G core network, which where they changed a bit the names of the elements. It's called now the AMF, Authentication Management Function, UMF, User Management Function, SMF, Session Management Function. So we implement the whole protocol stack, and the whole thing. So that's the second point. And the third point is that this whole software runs either in real time together with commercial software-defined radio platforms. For example, the USRPs. I'll say a bit more words about USRPs later. Or more recently, we also support more, let's say, carrier grade or more commercial products, like remote radio units from Benetel or AWS. I'll also say a bit more about those later. And of course, you can also run this in simulation. So that's what you will see in the demo coming up. You can run the whole software also in simulation on your own PC to do some experiments that don't require real time. So OpenAirInterface makes it feasible to build a fully compliant 4G and 5G network in a commodity x86-based computer. So basically the computers that you're using on your desktop, or most computers in data centers are also x86-based. So this is this is a key ingredient to what is the very popular Open Run developments right now. Yeah, so networks are changing and moving further and further to general purpose computing hardware, like you find in cloud data centers. So the objectives of this, and this has not changed for many years, and this is still the original objectives, is why. So OpenAirInterface was created by Eurocom. So it started as a project only within Eurocom. Today it's a really big project with international reach and a lot of contributions from outside of Eurocom. But the objective initially why we created this was to bridge the gap between academia and industry. So to provide a platform that is as close to industry as possible to any researcher who wants to use it for their own experiment. And that also makes the research that is being conducted with the help of this platform more interesting for industry, because it's very close to the real system. So that's one objective. The other objective is to embrace open source for 5G, so for 4G and 5G. So you find open source everywhere, and most of the internet infrastructure runs on, let's say, open source software. But mobile networks have been very resilient to this, mainly because of their business model. So the reason why these mobile technologies work well is because of the incentives the big players have in developing these networks. Yeah? So they usually they patent their technology. They bring these patents to the standardization, and they have an agreement with everyone in the standardization to share this patent pool. And that has worked, as you can see, has worked very, very well for them. But one of the objectives was, since we are a big believer in open source, at the beginning we were the only ones in this context. Now, today, you find a lot of people who are jumping on this open source train for 5G. We believed in open source from the beginning, and that was one reason why we created this. Yeah, and we also wanted to have a kind of a reference. I mean, that's still our objective, that still trying to achieve, is to provide a kind of reference implementation also for the industry, in addition to the standards. All right. So yeah, the success with OpenAirInterface started about 2010, when we had the first LTE connection, and so then a little bit later, 2014, we founded this OpenAirInterface Software Alliance, which is an individual entity outside of Eurocom, to help us with the management of the software, and also with the management of the community, which is still growing. So it's an entity that's an endowment fund, or in French, a fonds de dotation. So it is allowed to receive donations, and these donations help us to finance, have an engineering team here co-located with Eurocom that helps with the continuous integration, continuous development of the software, that provides support services to the community. And recently also these donations are actually used also to develop features and to drive the code forward. So we have in this fonds de dotation, we have strategic members. You'll see them here. So you'll find some very big names here. You find especially names from outside Europe here. So the only European partner is really Orange. Most of them are actually in the United States. So actually everyone except for Orange and Fujitsu are in the United States. And Fujitsu, as you know, is in Japan. So these are our main supporters in terms of money, but also these are the ones that actually decide on the direction and you know, the political roadmap of OpenAirInterface. One key point, or one of the things that this alliance has done is also to define an open source licensing model for the software. So I told you already that the 3GPP is governed by you know, by mostly patents, and patents and open source software don't go well together. So in fact, the classical open source licenses require that. So if you have a patent and you implement you know, this functionality in software, make it open source, basically you lose all the rights to your patent. And this is kind of a blocker for industry to be able to contribute to open source in the context of 3GPP. So the Alliance created a new open source licensing model, which we call the open source public license, which is a kind of which tries to marry these two worlds of open source and 3GPP. Yeah, so it is based mainly on the Apache 2 license, but it allows for it protects contributions that are patented, and we have received and this has actually been accepted quite well with industry. All right, so within the OpenAirInterface Software Alliance, there are many projects. I mentioned them before. So they're also hosted on different places. So for the radio access network, so the eNodeB, the UE, the gNodeB, the NRUE, this is all hosted on the Eurocom GitLab server under this repository here. The core network is it depends which part of the core network. So the 4G core network, the EPC, is mainly on GitHub. And the 5G core network is again on the Eurocom GitLab server. And Mosaic 5G, which is not yet, but is in the process of becoming a project of OSA, that is also hosted on Eurocom's GitLab server. And now I want to show you the different licenses that apply to these different parts of the software. So for the radio access network, we have this OAI public license that I just explained. And for most of the core network functionality today, we also use the OpenAir public license. Yeah, so especially for the in the 4G core network, the SP gateway uses the OAI public license, and basically all the 5G core network also uses the OAI public license. the only elements that don't use the OI public license are the 4G versions of the MME and the HSS. They use a 3-clause BSD license, which is even lighter, which is a very light license. And the reason this was done is because these two elements, the MME and the HSS, actually have been integrated in another bigger software project, which is called the Magma software, which is a project that is mainly driven by Facebook, by Facebook, to be exact, by Facebook Connectivity, which is a different entity. It's not the same, although connected, but it's not the same. Yes.
This public license you mentioned, do we have to request a specific access for from Eurecom or just registration mode?
No. So if you just want to, the code is freely available, is open. So to read the code, you don't need to request anything. You can just go to this website here and download it from there. And the license says if you use it only for research or education, then it's you don't have to worry about anything. It's absolutely free to use.
But if
yes.
I want to access the development branch or make any changes, then I would have to request some credentials probably.
Exactly. So what you have, if you want to contribute to the code, then you first have to sign the contributor license agreement.
Okay.
This is very common with all open source projects. So that basically says that any code you contribute back to the project will keep the same license.
Okay. Just to be elaborate, I already tried. I have taken a look at Mosaic 5G, and I tried downloading the core network and RAN part of OAI, which I also configured along with USRP and Raspberry Pi. But some of in my further research work, I would like to make some changes in the flex RAN part or some changes at even the RAN part and components. So for that, I should have to request this contractual things as you mentioned,
yes.
right?
Okay. Yes. So
and I only have experience up till LT version release 13 and 14. So you will be also today explaining about 5G new radio, right?
Yes. That's just next year.
Okay.
I just wanted to add here. So I don't know if Navid is on the call already, but he will certainly say about this something later. The Mosaic 5G, we still have to set up the contributor license agreement.
Okay.
So this is new. I mean, this project has not been part of OSA previously. Now it's part of OSA, and so we need to set up the contributor license agreement. So this is in the pipeline. It's not available on the website yet, but it will be very soon.
Okay, thank you.
So hello, this is Robert, and I'm the PhD student of Navid, and I just wanted to clarify. So if you want to make changes yourself to FlexRun or to OAI, and you just keep it for yourself, then you can make any changes that you want. You only need to sign the contributor license if you want to actually contribute back. So if you want to make a merge request or something, but for yourself, you can do whatever you want with the code if you have already access.
Okay, thank you for clarification.
Yeah, thanks, Robert. That's actually important. Thanks, I forgot this. Okay, so let's move on here because I'm running very late in time. I just realized. Robert, you wanted to start at 2, no? No, at 2:15. 20 minutes.
Yeah, we said 2:15. Yeah. But
okay, good.
If you can also have 10 minutes more if you want.
Okay. All right, so I want to talk about the 5G new radio and the development status today. Can I have a pointer here? Yes. Okay. So yeah, before I tell you about the status, I just want to say a few words about the different deployment options of 5G today. So the two main deployment options that you find today and that operators have deployed or are deploying is either the non-standalone or the standalone version. Non-standalone is called like this because it heavily relies on the existing LTE network. So you need in order to operate 5G non-standalone, you need a 4G network. You need a 4G eNodeB, which is connected to the 4G core network, the 4G EPC. And the 5G cell is basically the GNodeB is basically a slave to the 4G eNodeB. Okay, and so a phone can only connect to 5G once it is connected to 4G, and it detects that it is within the coverage of a 5G cell. Yeah, then the phone will send measurements back to the eNodeB, and the eNodeB will configure the 5G cell, and the UE will connect to the 5G cell. But at in the core network is still the 4G core network. So traffic and the traffic can either be redirected over this S1 U interface or alternatively also by X2U, okay, which is not depicted here. Yeah, in OpenAirInterface, we actually use we redirect the traffic once the phone is connected to the 5G cell. We redirect the traffic over S1U to the user. Okay, so this is the non-standalone, also called eNDC for eUture NR dual connectivity. Yeah, because it uses the dual connectivity feature that already existed in LTE before. And so this is the version that's being mostly deployed today. I think 99% of today's deployment are non-standalone. I think only in the United States they have started to deploy a standalone network. So standalone means that, as the name suggests, that you can run the 5G network without the help of a 4G network. And it also requires that you behind you have a 5G core network. Okay, so this interface changes. Instead of S1, you have NG, and but basically the GNodeB itself is more or less the same as you have in non-standalone. It needs to do a little bit more, so because it needs to handle the control plane now too, but otherwise it's more or less the same. With respect to development in OpenAirInterface, there was an initial phase which we called the NoS1 mode, which is a kind of an extension of what we had in LTE, which is somewhere in between the non-standalone and standalone mode, in the sense that it allows you to operate the GNodeB without any core network and without any eNodeB. But that also means it will only work with the OAI, so it will not work with any commercial devices. But this mode is still there, and it's good for testing. You know, if in your research the only thing you're interested is the radio access network, you know, this is still a good mode for testing. The phase 2, which we completed last summer, is the complete eNDC non-standalone with an off-the-shelf UE. Okay, and right now we're working on standalone. And I'll say a few more words about that in a minute. So as I said, non-standalone is working since last summer. Initially we had very low throughput, but recently, thanks to Robert, we have a rather good throughput. I mean, it's not yet at the at a level that you find in commercial devices, but that's mainly due because we use only a smaller bandwidth. We use 40 megahertz bandwidth. In TDD with 30 kilohertz subcarrier spacing. So the 50 megabits is about, let's say, 50% of what you can ideally get with this configuration. Okay. Actually, we're not single user anymore. I should change this. We also support multiple users. And as I said, there's no split bearer, so traffic is completely redirected to the 5G cell. So in theory, here in this non-standalone setup, you can also aggregate traffic from both 4G and 5G, but we don't do it. The OER UE currently only supports this NOS1 mode. Okay, so we do not today have a UE that supports full non-standalone mode, so that is able to connect to both 4G and 5G. Yeah, let me skip that. Let me rather talk about the roadmap. So we're targeting to improve the throughput. So as I said, the maximum that we can have in this setup is 100 megabits. So that means we have to make the high MCS work as well. We also have to work a bit on the uplink, and we want to bring this up to 200 megabits by doubling basically the bandwidth. We're also working on FR2, so basically all the tests that we're doing today is FR1, that means below 6 gigahertz. FR2 is a different topic that I could talk about for a long time too, but I won't. And we're also in the second quarter this year, we're also planning to include MIMO support. Very basic MIMO support is already there. But it doesn't work yet with the COTS UE, and this should again increase the throughput that we can get. Now, going to standalone. Okay, so this is ongoing development. The phase 3 that I showed before. So in standalone, basically all the control plane is transported over the 5G network as well. And that also includes the very first broadcast messages, which is called the system information broadcast. No, actually it's called the system information block 1, but it is a broadcast message. So it is sent to all users in the cell, and it contains the basic configuration that allows a user to connect to the network. Okay, so this is implemented, and we can also already see this with an off-the-shelf UE. So you see down here, this is an experiment that has been done that shows that so this is not a smartphone, but this is a module. So you interface with the AT commands, and this command here, this AT plus COPS, shows you shows you the results of the cell search. And so this shows that the cell that we have, the 5G cell that we have set up, shows up in the cell search. So this last number here, the 12 here, means that it's a 5G NR. Yes. 7 I think means LTE, and I think 2 means 3G. So this experiment was done in Portugal. So you see the standard operators of Portugal and this additional cell from OpenAir. So we haven't completed the complete attachment with the UE yet, but we're not far away from that. So the initial access procedure is more or less in place. We also have on the higher layer the radio resource control, and the NAS is completed, but there's a little bit of development missing in between these two, and we hope we'll be able to finish this by the end of February, at least in simulation. And the plan is by the end of March is to have a demo with the complete 5G initial access with a off-the-shelf phone and some initial user plane traffic. All right. Yeah, I'm running out of time, so I will skip over that. Yeah, I want to say one word about the hardware targets, since many of you are new to OpenAirInterface and probably also new to software-defined radios in general. Let me mention a few words about the hardware targets. Historically, well, historically, I don't know, but no, let's put it differently. The most popular hardware platform that people use for OpenAirInterface is the USRP, Universal Software Radio Peripheral. So that's a device that has been developed initially by a startup in the United States called Ethos Research. And a few years back, they were bought by National Instruments. It's basically a device that you can plug into your PC, and that gives you, you know, a software-defined radio that you can play with. Didn't I have a picture here too? Oh, it's on the hidden slide. Okay, let me because there's additional things on there that I didn't want to show. Anyway, these are the devices, the USRPs. They look like this. So you have the B210 on the right. This is the X310 and the N310 here. Was there a comment or a question? Okay, so the B210 is the oldest one. It's also the cheapest one. It operates over USB 3, and we have used this in the past mainly for LTE, but it can also be used for 5G as long as you limit yourself to 40 megahertz bandwidth. Okay, and SISO. Yeah, so it will not work. It can work in 20 megahertz MIMO or in 40 megahertz SISO. If you want more bandwidth, you can use the X310, which can go up to 80 megahertz. Or the latest model is the N310, which can, in theory, go up to 4x4 MIMO with 100 megahertz. However, I have to add that these are ideal values that we have not quite achieved to get out with OpenAirInterface. Okay. Any questions so far? Someone is unmuted, and I always have the feeling he wants to ask a question. I can't see who it is. Okay. All right, so let me use the last few minutes here to say a few words about cloud native and Open RAN development. So there is a trend in mobile to go from a more traditional radio access network to an open radio access network, and what people mean with or virtualized. So this has had multiple names. So cloud native, virtualized RAN, Open RAN. But basically, what people mean with that is that they basically want to get more control over the radio access network, and this is done by splitting the functionality of the baseband unit that typically today you buy from Nokia or Ericsson or Huawei, by splitting this into multiple units. So the CU, the centralized unit, the DU, distributed unit, and the radio unit, and defining open interfaces between them. So between the DU and the RU, you have the open front haul, and between the DU and the CU, you have the open mid haul. And potentially, these units can run so the DU will typically run in an edge cloud environment, so not too far away from the base station, but the CU can potentially run somewhere in the cloud, maybe not at the other end of the world, but in a cloud that's you know in the department or in the. So this makes it possible to gain more control over the network, to basically run functionality as software, and to benefit from all the different developments in software-defined networking that have been achieved over the recent years. And it also operators like this approach because they can also be able to mix and match elements from different vendors. So how does OpenAirInterface fit into this picture? So OpenAirInterface, as it is software and it is open source, it can basically implement both CU and DU. Not really the RU, well, some parts of the RU maybe, but not the complete RU. But it's good for the CU and DU, and basically covers the whole radio network part and also the core network. But Open Run is more than that. So in order to run the software in a virtualized environment, you need a virtualized infrastructure and technologies. So you need to be able to run your code in an environment like this. So for example, using Docker, you can run this on the Kubernetes platform or an OpenShift platform. You need, if you want real control over the different elements, there are these new interfaces that have been defined, which are called E2, which allows a different, an intelligent controller to control certain elements of the radio interface. And here there are other software projects that can handle this. One of them will be covered later today. One of them is part of Mosaic 5G, and it's called FlexRun. And then on top of that, you have other software tools, ONUP, Open Source Mano, or Cube 5G that help you to orchestrate and automate this network. All right, I'm running out of time here. So maybe the only thing I want to say today is that we have OpenAirInterface is ready for such Open Run and cloud native deployments. So there's a separate GitHub repository that contains the different everything you need to build these elements. And we have today a platform at Eurocom that we use as a test. Let me show this here. So basically this is the Eurocom building, and we have deployed today radios on the outside here of the building as well as on the inside, and everything is connected to the server room. And in this server room we have high performance switches and high performance computing elements that run this Red Hat OpenShift container platform. And we have packaged our different components, LTE and NRRun, EPC and 5G, and some mobile edge computing functions. We've packaged them accordingly so that we can run them on this OpenShift platform. So this is also connected. This is actually part of a bigger project which is called 5G Eve, and it's also connected to a centralized exchange point, and is part of a bigger network with different experimental network deployed by different partners of this project. Yeah, this is a picture of the radio, of the antenna that we have on our roof. So that's actually our based on the N310 and is used for 3.5 gigahertz. So you see the USRPs down here. We have a power amplifier, and it's driving these actually the 3.5 gigahertz antennas are the small antennas at the side here. You the big antenna in the middle is for LTE at 2.6 gigahertz and 700 megahertz. As I mentioned in the beginning, we also have now we also deploy commercial radio heads. They use the so-called ORAN interface to interface with our software. We've already deployed this one from AW2S on our roof, and the one from Benetel is deployed indoors. We're also doing some experimentation with millimeter wave. So this is frequency range 2, but this is for the moment still in the lab and not quite ready to be deployed yet. All right, and let me finish with this slide here. So the key takeaways from what I just explained is that OpenAirInterface is one of the most advanced solutions for Open RAN and cloud native deployments. So it's ready for integration with ONAP. It runs on Kubernetes container platform, and it runs on Kube5G. We still have some work to do with the implementing some of the interfaces to allow for full functionality of Open RAN. So, for example, we need to complete the frontal interface, but also the E2 interfaces that allow for connection of an intelligent controller. And we have infrastructure at Eurocom. This infrastructure is open. So if someone of you wants to do some experimentation at Eurocom, it is possible. If we set up a collaboration, then you can access our equipment remotely. We can give you access, you're more than welcome to get in touch with me if that's something that interests you, and I would be happy to find some ways to collaborate on this. We can always, in OpenAirInterface, we can always use help with the development and testing, and of course, we're always happy to see some new experimenters and experiments. Okay, I'm over time already, so I'll stop here and maybe take a few questions.
Hello.
Yes, sorry, that was loud.
Hello. Actually, I have a simple question. All of these deployment is all in one, like Kubernetes, OpenStack, OpenRAN. It is all in one machine or different? Like you saw some one slide, like OpenStack, then OpenAirInterface, and after OSM. Before actually. All of this deployment is all in one, or you deploy
this picture here.
This one actually, yeah.
No. This I don't think you can set up all of this in a single machine. Anyway, this is.
For curiosity, actually, I asked. This one is actually mainly separately you deploy, right? Eurocom deploy. Like OpenStack is another machine, OSM in another machine. That's why you deploy it, or all of this in all-in-one machine?
No, this is not deployed in one machine. It also, I have to say that we have not. I mean, what we have deployed today is OpenAirInterface. So everything you see in the blue box on an OpenShift platform together with ONAP. Okay, with ONAP orchestration, but this was not done in the same machine. So this was run on multiple. I mean, each of these elements runs in a different container, and potentially a different machine. We have not yet integrated with these projects that are listed here: the SD-RAN, Ether, or CORD. We did integrate.
OSM also, right? You deploy it.
OSM,
yeah.
I don't know. Maybe
I can say something, Florian.
Yes. Go ahead.
So, in terms of deployment scenarios, like how you can deploy different network entities across different machines, you will be having another presentation of Kube5G. Let's say a bit later, but I can give you just few examples. So we have been working on different scenarios. We call them blueprint. For instance, you could have on the core network, you can have an all-in-one or disaggregated deployment. So all-in-one includes all of the core network into the same machine, right?
Yeah,
and
yeah.
Disaggregated, for instance, you can deploy it in different machines, whether physical or virtual, right?
Yeah, yeah.
At your choice.
Okay.
The same holds for the RAN. So Osama will give you the blueprints we already developed and available for you to just plug and play and deploy. Knowing that from the deployment perspective, everything is possible, but from the performance perspective, you need to dimension the resources so that your network is properly working and serving the user. So these are two different set of questions, right?
Okay, yeah.
So, meaning that if you would like, for the simplicity of your research, you want to deploy all-in-one. For instance, Robert is going to show you an example with the simulators, right? You don't need the RF. You can deploy everything in one machine and start experimenting, gathering data and process it, right? But if you want to scale, you want to have a real system, then you need let's say powerful machines, right, to distribute the workload and have a right performance.
Okay. Thank you for clarification. Thanks.
You're welcome.
Yeah.
Any other question? Okay. Robert, you want to take over?
Yes. Hello. I can take it. So hello everybody. My name is Robert. I'm a PhD student of MSCA-ITN, and I prepared just 1-2 slides to show some things, and then the rest will be hands-on. So actually, let me share my screen if I can. This. Can you see the screen?
Yes, I can see myself.
So, and maybe now you hear me also better. Yes. So I have this. So what I will be doing in the next 30-40 minutes before the break will be like some short hands-on with OpenAirInterface. So we will start from the basics because I don't know what is your level and so on. So I really would like to start how to get the code, because this was the question before. Then maybe for those who already looked into it, probably you immediately have the question, where do I find what and how to modify the code? So I will just go through the structure and give you some pointers where you could find what, because when I started to work with OpenAirInterface a couple of years ago, then it was not straightforward, I found. Then we will just go and install the dependencies. I have already done this. I will show you how to do, and then how you can compile it. And we will actually run the 5G simulator. And the simulator, so that first of all, you could also follow yourself and maybe try this right away. I think you can run this actually on any computer. It will just be slow if your computer is not super powerful, but you could download and then install all the dependencies and then just run it. And then the last thing is how you could maybe see some physical channels if you are interested to research on the file layers. And I have to already make the disclaimer that I had some problems, so it didn't show properly, but we can see how it should look like and what you could see. And anyways, just to give you a brief outline of what will come. And actually, so I have two pictures that I will show you, but we will first look into the 5G RF simulator, because we were talking about 5G, and this is maybe what you're also more interested in. But then I will also briefly cover the L2 simulator, point out the differences, and this is what we will be using later when we will discuss about FlexRun. And so later we will discuss about FlexRun. So if you have any questions about FlexRun, I would like to ask you to keep them for later, maybe note them down before you forget. On the other hand, if you have basic questions, if you maybe already work with OAI, then please just ask me. And then maybe we can briefly go over your questions that you might have. So with that said, let's start. The first thing, and I already started, so the first thing would be to clone the thing. So OpenAirInterface is open, so you can just download. So this would be the address of the GitLab. Maybe it was also in the slides. And what is important is that I recommend that you always use the develop branch, because then you have all the newest things. If you were just in master, then you would not actually have 5G, because I think the 5G changes have only been merged to develop, and master is always a couple of months behind. So I'm not sure whether 5G is there or there is only some basic things. So, and then we can, I was already in OpenAirInterface, but that's no problem. OpenAirInterface. So, and then I'm in the OpenAirInterface directory, and you already see a lot of things. So let me just briefly go over it so that you get a basic idea of what would be where. So CI scripts, the first is for the continuous integration. So there is a team also here in Eurocom that continuously tests not the full OpenAirInterface, but at least certain test cases that are always run, for example, whether the basic 5G functionality works or 4G, so there are all the scripts. And also, if you ever want to deploy something and you already had some configuration files, it's always useful to go in there and check the configuration files that they have in there, because this is what OAI is tested with. So the next thing is then the CMake targets, which is everything related to building the things. And if you know CMake, then I can already also maybe point this out, that the CMake lists.txt in OAI is not top level, it's in this directory, and from there it is built. Then there is common, where you have generic, kind of generic stuff, so some helper libraries, the so-called T-traces that helps you if you want to maybe see the transport blocks on the MAC layer within Wireshark, because this is one thing that you can do. And there is timers and so on. Then there is documentation. There is for Docker, for the for cloud native stuff and so on. It's not so my thing, so I don't really know what's below there. Executables is the executables for 5G, and FAPI is the NFAPI library that is also used with an OpenAirInterface. I will briefly cover this later. So, and until here, it was not very interesting, and maybe the more interesting things are OpenAir 1, 2, and 3. And let me briefly just go here. So maybe you know and have already seen this. So in 5G, you have the different layers, SDAP, PDCP, RSE, MAC, and PHY, and actually also the RRC. And you can assume that the PHY is layer 1, and everything above, including, well, or until SDAP is kind of layer 2, RRC is maybe more layer 3, but for this, I tell you this for the sake of these directories. In OpenAir 1, you will find everything that is related to the physical layer. So can I hide this? Hide doesn't work. Cool. Let me do it like this. So I don't know this part of the code in detail, but you could look, this would be LTE file layer. Then you probably also in there you have for NR. So maybe let's just have a brief look and take this time. So PHY, and then well, yeah, for estimation, LTE, and you see already here's the things that are related to NR. I think in transport is everything for the transport channels, and so on. So this is an OpenAir 1, everything that is for physical layer. Then we have OpenAir 2, where you have, as I already said before, everything that is kind of in the base station. So actually the interesting, I mean, you can see here the RRC, so under OpenAir 2 RRC, and then on there you would have for the LTE and for NR, the NR layers. So here you have LTE and there you have NR and also something for the UE. And if you were searching for the other layers, that is, for example, the MAC, then this would actually be an OpenAir layer 2. And then you can see you have the LTE MAC and the NR MAC for G-Node B and for UE and common. There are the RLC and the PDCP. SDAP was in another, I mean, was above just an OpenAir 2. And you have also the NR counterparts. So just to give you first pointers, if you were looking into this, and finally you have OpenAir 3, where you would, for example, have GTP, which is used to transport data to the core network, where you would have S1AP, I mean, S1AP, sorry, is used for the control messaging between the base station and the MME, which is the control entity in the core network and LTE. And then I think an NR is NGAP and some other things like the SCTP, which is used for the base station, NAS, which is the actually the traffic that is exchanged between the UE and the core network and so on. So OpenAir 1 is PHY, OpenAir 2 is all the layers from MAC to RRC, OpenAir 3 is more with everything that is kind of related to a core network, let's say like this. And then finally, the last one was targets, where you would actually have things like the different SDRs, I think it's under Arch. So let's maybe have a look, since Florian also mentioned this. So you can see here you have the USRP family that Florian already mentioned. You have the RF simulator here, which we will be using in a moment. And then you have some other like Blade RF, which is another Iris and so on. But typically, I mean, if you would buy your best bet is to go with USRP, because this is also what is usually used in OpenAirInterface. Yes, are there maybe some questions here for especially people who have already used it? No, so okay, so this just that you have a first impression, then maybe let's go on and just have a brief look at how you would install dependencies and how you would compile everything. So actually everything is kind of done by a wrapper that sits on top of CMake.txt, which is this build OAI script, which kind of...
There is a question of Baltica.
Yes.
Yeah, actually, I am actually asking about the RF simulator. This is RF simulator is 5G UV and 5G G-Node B, right? This UV is 5G based or normal 4G UV?
Actually, the RF simulator works for both 4G and 5G. As far as I know, I think there's no hard dependency actually. So I will, well, I can do this now. So this is for 5G, but in 4G
yeah,
it looks the same.
5G is deep. Actually, I am looking UV also 5G based, right?
Sorry?
UV 5G. This UV is 5G based or 4G?
Yeah. So actually, what I mean, I can show you also for building. But so what you would typically do, there are separate executables for the G-Node B and the E-Node B, so the base station for 5G and 4G, for those who don't know. And then there is a UE version that is 4G and a UE version that is 5G. So you can build those separately. We will see this in a moment when I will start this, just to give you an impression. And the RF simulator does not have, as far as I know, any dependency on any radio access technology, be it 4G or 5G. I think this is this is implemented like a generic SDR, as if you were using USRP. So the G-Node B is not aware that there's actually the RF simulator running below. And then you can just send things through there. And as I've also mentioned here, there are some channel models that you could use. I will briefly show this, but yeah, I mean, the RF simulator is something that is kind of separated, and you can either run 4G or 5G traffic over there. Does this answer your question?
Okay, thank you. Yeah.
Okay, is there another question? Because otherwise, so as I said, there is the build OAI script, and you have a lot of options. And in the beginning, I also found it, no, maybe, I mean, not necessarily confusing. I mean, in the end, there are a lot of things that you can do. So, of course, maybe there are a lot of options, but what you will typically do is, if you run up to Ubuntu 18 or all other distributions, you need this capital I to build, to install all the dependencies. So if I was running this, then it would tell me Ubuntu 20 is not supported because there's actually a separate installation script for Ubuntu 20. But this capital I would be what you would be needing if you were just installing the dependencies up front. So, and actually there, so here is the example. So this is what you would need once, and then if you installed it and you just use the same machine, then you would never use it again. And then the interesting options that might be used is, actually there are two different versions of clean, and I don't know what is the exact difference, but you just put the two. And now what I just said, there is the eNode B, which would be to build the 4G version of the base station. There is the GNode B, which is to build the 5G version of the base station. There is the UE, which is the 4G UE. And there is the NRUE, which would be for the 5G UE. So yes, so you could just put all of them and it would build all of them. And what you will also typically need is the W parameter to build for a specific SDR. So if you were also using an SDR, you would just put a -W use RP to build for that one. For the RF simulator, you don't need this at all. This is built by default. And then also one thing that I wanted to tell you, you typically probably want to use Ninja, which is a build system below CMake. Let me put it like this, it's a faster version of what was used before in general for compiling and also in OAI. So what you typically want to do is to just use Ninja all the time, because otherwise your builds can be quite slow. So, and this is kind of the typical complete list that you might need for the NR scope that we will use later. There is also something that you might, where was the, I think there was some library and then it says NR scope. I don't see it now, but yeah. I mean, to put it short, unless you have some really specific things, usually this is what you want to have. And if you have more specific things, then maybe have a look through here. But from my experience with those, you're already good. And this is it. So, and I, of course, in order to not make you wait too long, I already did this. So this is the OpenAirInterface repository that I usually work on. So then we go into CMake targets. And by the way, there's also one specificity. By the way, what I forgot, there is also, because this might be interesting for you, the capital P, which is for building all 5 simulators. Yes, sorry. So, but anyway, so this everything would be done in CMake targets, and it would then create run build directory where you would have all these artifacts. So as we saw before, just to close the circle, LTE soft modem is the 4G base station, LTE UE soft modem is the 4G UE, NR soft modem, sorry here, and UE soft modem correspondingly. And what we could do now is to just run the RF simulator. So I kind of prepared this already. There is some documentation that you can read for the RF simulator, which I think is under OpenAirInterface doc and, oh no, sorry, it's probably in OpenAirInterface targets architecture RF simulator, so where the RF simulator was. But basically, in a nutshell, what I'm doing here is I run it as sudo, which you need because the base station sets some special parameters for real-time processing and so on. Then I use, because I'm a bit lazy, an old version of telling the RF simulator to actually be run. If you look into the documentation, it would be a bit differently, but not wildly. So then I have the NR soft modem executable. You always have to give this parameter capital O and a configuration file. So if you run the RF simulator, and I think it also says this in the documentation, you would always be using that one, which is for a G-Node B in band 78, which is a TDD band, which is standardized by 3GPP over a bandwidth of 106 resource block, which I think is 40 megahertz, but I'm not entirely sure. And also N300 family of USRPs. Anyway, so this is just for threading. This is another option, probably superfluous, the first RF simulator, because I'm saying RF simulator here. Now we come to this No S1 mode, which I showed, which Florian already explained. But as he said before, you have the G-Node B and the UE, and they run without any core network. So we will see in a moment there are network interface on the G-Node B and network interface on the UE side, where you can kind of inject traffic, and there is no core network. And in other words too, this No S1 mode typically only makes sense if you use the UE from OpenAirInterface. You wouldn't be able to use an SDR and then No S1 mode with a commercial phone, like your own phone, which for example you could do for 4G at least. And but this wouldn't work, because then the terminal would try to contact the core network, but there is no core network. So No S1 typically only when you do simulation or something like this. Phi test is something that for the scheduler to give some configuration, doesn't matter here, and the D is for the scope that I will do show you later. So long story short, I will start the base station. There is some errors, which is not a big deal and which will probably sooner than later disappear. And on the other side, I run the same thing for the UE. So again, sudo RF simulator, the NR UE soft modem this time for RF sim, No S1, no kernel mod. Actually, I'm not entirely sure what this means. Phi test, as I said before. We would also run this, and then we would see that RF simulator success, and it connects, and yes, now we don't have this. And so now the thing runs. So you have the RF simulator that transports all the samples that are output by the file layers on the two ends. So here between the UE, which runs on the right side of in my screen, and G-Node B on the left side, and this is what actually is already running now right here. And to just give you some or make some sense of what you see here. So first of all, you see periodically that there is one UE that is connected at the base station with the RNTI 1234, which is just the identifier of a UE. So here it's fixed. Typically it would be random, but every phone has this. Then you have DL SCH rounds and UL SCH rounds, which means the transmissions and retransmission numbers. So the first one would be how many initial transmissions have been done on the MAC layer to UE, UL SCH in the other direction, and the others here are retransmission attempts. And actually now, as you can see, the 60 is because when we were running this in the beginning, but otherwise you don't have any errors. So now we always have 6660 and 00, but the first number increases from one time to the next time because the RF simulator has no channel model, so everything runs smoothly and everything runs fine. And then this is the number of bytes that have been scheduled in the MAC, and LCID actually means how many data is transmitted between both ends. So, and this is running happily now, and what we could do is just inject some traffic, which I would also like to briefly do, because then you get a better idea. So if I run ifconfig, for, I hope most know this, so which shows the Linux interfaces, and we actually have one interface for the eNode B and one interface for the UE. And the eNode B has the IP address 10.0.1.1, and the UE has the IP address 10.0.1.2. And what we could do now is we could inject traffic on both sides and see this. So what I will do is I will just make a TCP dump, which just will dump all the packets that arrive. And I will do this in the downlink. So I will just check all the traffic that comes out on the UE side. So this is what I will do here. And I will then ping the UE. So I will ping, but not this one. So I will ping through the interface of the eNodeB, which is very important. Otherwise, the Linux would just circumvent going through the simulator and just send it directly. So we go into the eNodeB here, and we send it to the IP address of the UE, and we do this every 10 times in a second, every 100 milliseconds. And I do this with ping, so there is a higher throughput. And now you might also be a bit confused. You don't get any ping replies because there is some limitation. You could run the eNodeB and the UE on 2 different machines, then it would run slower, but at the same time you could actually ping and get a response back. But the ping times would be probably rather high. But with that said, anyway, we see that there are some transmissions because we sent it here on the eNodeB side. By the way, I don't know why, but the interface is eNodeB, but we are running the gNodeB. Sorry. But we see on the right side there are the ICMP echo requests, so the ping requests that are arriving, and every 100 milliseconds a new packet, so constantly. And what we can also now see is that there are constantly more and more bytes sent for the UE in the downlink. And we could do the same thing, and well, that's the first thing that you would do. And if you're already here, then you would basically be ready to maybe try modify the code, do some things. And there is one more thing that I wanted to show you, because also we are just not that much before the break. So I explained everything like this. By the way, is there a question? I explained a lot of things. I explained where are the layers, where you can find this in the code, how to compile, how to run, and so on. Before I show the last thing, is there a question here? Yes.
I have a question, Robert.
Yes, please.
Why? I didn't understand. Why the ping? What's the limitation with the ping? Why can't you?
Well, there is. I don't know the exact reason. Partly because I was lazy and never checked, but there is some limitation that you originate the ping packet on the machine where you have. Maybe somebody in the audience knows. I don't know. I mean, it's a limitation. If you were running this on 2 separate hosts, you would get the ping packet back. Yeah, maybe the reason is that I could imagine that since the ping packet is probably delivered out of the RF simulator, so it doesn't come back through the eNodeB interface. Maybe that's why we don't receive it, but just on loopback. Could be.
I think the limitation is more about the networking. We need to manipulate a little bit IP tables.
Yeah,
get the packet back to the stack, because the packet is crossing the same stack.
So what you're saying is the packet in one direction it goes through the OAI stack, but in the other direction it might not go through the OAI stack.
Yeah, but we could analyze this by checking if the ICMP echo request has been received on the UE side. And then the loopback is the issue. We need to tell to the kernel to ask for the packet again.
Yeah, so I'm not entirely sure, but I tested this myself. We run, also for the audience, in case you don't believe this, just take 2 computers, install, set the IP address, by the way, that was here in the beginning of the UE, and then you will get the ping packet back. Are there any other questions, even questions where you think this might not be, just ask me anything if you have a question.
Robert, I have a question.
Yes.
The TCP dump,
yes,
is dumping on the UE side or on the eNodeB side?
On the UE side, so here
and the
interface,
ping is sent on the eNodeB side, correct?
Yes, so we use
so
the
it
interface.
Means that the UE receives the request, it does not generate the reply.
Yes, so this is what we what we see.
Exactly.
So any other question from the audience of the winter school? No. Okay, no problem. The last thing that I wanted to show you before I go actually to the other 4G demonstration with the simulator is that, as I have said before, you could now have some channel models in the RF simulator. And as we have seen, or as you probably have understood, is that there are no retransmissions. So for the downlink, it's always 60 because this was in the beginning. In uplink, you just have 0 all the time, which indicates that there is no noise and there is no wrong interpretation of the channel. I mean, sorry, there's no noise on the channel. There's no, I mean, the channel is perfect. Let's say in this terms, there's a perfect channel between the eNodeB and the UE, which typically is not the case. And the only thing that I wanted to show you now is that we could actually load some channel model and give some noise. So we here RF simulator options, and we want to set a channel model, and then we set by default it's an additive white Gaussian noise that is just put onto all the symbols that are sent there, and then we give an SNR. Well, actually, about the meaning, I'm not so sure because I'm typically not working on the physical layer, but for sure you find it in the documentation. And I will also run the NR scope just to give you an impression what this would do. And in the other direction, I won't do anything, but I wanted to still add the scope. So now I'm running again the NR soft modem, so the GNodeB, with the scope that you have already seen popping up. I will also do the same on the other side. And actually, I don't know why I think maybe it's a local problem. But what I wanted to point out, and if you have a question, maybe Florian can answer. I'm not so fit with this, but for example, you would see then here the constellation that is used for the modulation. So, and for those who know, what we use in the simulator here and the configuration of the scheduler is a fixed MCS. So it's always QPSK. So we have this constellation diagram and we see that there is some noise. So it's a bit blurred. And if we would give more noise, do we actually already have some retransmissions? No, but we can give maybe some more noise and then we should see some retransmissions. At some point I tried this, and let's just try like this and maybe we'll see some retransmissions now. So now you see it's much worse. It's more like one bubble and not the QPSK, the clean thing that we had before, and we see here that there are actually retransmissions all the time in uplink. And what we also see is that now everything is running much slower because you use this RF simulator. So with that said, when would you use this RF simulator actually? And what is the point of all of this? So you would have a standard compliant GNodeB, a standard compliant UE. And especially the GNodeB can be used with a phone. So we didn't show you a video, but if you watch online, or maybe Florian has a link, that you can see that you can connect a phone, you can make some iPod, you can watch YouTube or whatever. Connect a commercial phone, maybe even your phone if you have a 5G ready phone, to the base station and work this. Use it. And so all the layers here are standard compliant to NR, but it might be difficult if you want to modify and try something in the physical layer. So in this case, you could use the UE and have actually a standard compliant 5G stack, then virtualize or simulate an RF channel with different channel models, and in the simplest case, just have an additive white Gaussian noise. and you could use this to maybe modify the code if you want to try some new coding scheme. You could use this to modify and try things in the physical layer. You could, if you're working on modeling of channels, you could theoretically use this to model this and then run everything on a standard compliant, unless you modified, of course, standard compliant 5G stack. So this would be the interest of this. The disadvantage at the same on the other side is, of course, that there is some overhead with this, because you're always modeling the complete channel. The physical layer, especially in 5G, is very resource intensive. Everything is quite slow. I think you can have multiple UEs with the RF simulator, but it will be very slow. And if you are actually interested into the higher layers, for example, if you're more interested into modifying something in the Mac, for example, another scheduler, then it would be better to not use this RF simulator. And this brings me to actually the last part, which we will also use later with FlexRun, where I will now speak, or later also speak, about the L2 simulator, which is actually 4G. So in 5G, there is not the L2 simulator, but in the L2 simulator, you can see this. If I go back once, here you have the 5 for the 5G RF simulator. In the 4G L2 simulator, you have the MAC. So as you maybe have already guessed, the L2 simulator refers to the fact that everything is on layer 2 and not below and on the PHY. So there is no RF simulator. There is the MAC, which actually outputs messages. And this is the NFAPI, I think, that I already mentioned before. So, and then these messages are sent between the eNode B and the UE. And actually, if you want to know a little bit more in detail, typically, well, not typically, all the time, the MAC and the PHY, they always use NFAPI messages to communicate with each other. So this is kind of a standard to have a uniform representation of what needs to be transmitted between MAC and PHY. And instead of sending the messages from the MAC to the PHY, here we send these messages from the MAC of the eNode B to the MAC of the UE. And this way, then you can circumvent the resource-intensive RF simulator and the resource-intensive physical layer of 4G or 5G, and then have, for example, multiple UEs. And this is what I would like to show you. And by the way, also one of the things, so then you're, I mean, you could use a core network with the RF simulator, but it doesn't make sense. So I had network interfaces on both ends of eNode B and UE, and this is what we just discussed with the ping. Here with the L2 simulator, you maybe even want to use a core network, and you could do this. So this is the S1 mode. And yes, and I will briefly show you how this would work so that you just get an impression of what this is, and we will use it later. So I will just stop this here. Now what we need and what I already prepared is a core network. So the HSS, which is the entity that has all the subscription information. Sorry, wrong password. Then the MME, which does all the setting, I mean, control information. The mobility and management entity is the name actually. And then the SP gateway is the serving and packet data network gateway, which is everything related to data forwarding, which doesn't go through the MME. So for those who know a little bit the core network, maybe know how this looks like if they didn't use OAI before. And I already built this before, and I will just now, from the same directory, start the LTE soft modem this time. So I will do this here. What you would typically need to do, by the way, but I don't want to go too much into details, is to set up also some subscription information for the UE, which I have prepared before and for which you find a tutorial. And yeah, there are some things that you might need to send up. But on the other hand, we can start the UE soft modem, and it actually says that it will connect 4 UEs. So if I start this now, then it takes some time, but it will set this up. I will already prepare so that we can have some traffic. And there's 1, 2, 3, 4 UEs that got connected. And then, for example, you could also watch this in Wireshark and have the exchange of messages between the UE and the core network and all these type of things. And what I want to show you now actually basically is that we can just listen on 4 different interfaces. So this is a script that I prepared before, which will just do iperf and bind for each on the IP addresses of the UE. So we can, by the way, look this here. I'm now on the machine that runs the UE. So we have 4 UEs this time. Before we had only 1, now we have 4. I have the script to listen on the interfaces for all the 4 UEs. And actually, what is a good thing, I will show you the complete throughput, but what I learned is that usually for memory management reasons, it's always a good thing to just send some traffic to one UE, which would already be good. So we send 1 megabit of traffic, but we need to send this, of course, the first UE's IP address ends on 2. And we see there is some traffic. So we send 1 megabit from the core network, which is on the machine Fumarola, which is somewhere in the Eurocom network. This is on my local machine, receive this traffic. And we could now, of course, do this for UEs like this. And then we would have an LTE network, a complete network actually. So also with the core network with multiple UEs. And we send traffic according to the bandwidth, with the full throughput and everything. With that said, we will go a little bit more into details here later. I just wanted to show you this, that you could also install everything, set this simulator up, have a compliant 4G simulator, and make similar modifications to the stack or whatever you want to implement and use it like this. Are there any questions?
Is it possible to run all the instances on one machine?
Yes. So you can run everything. There is a similar limitation with what we just discussed before with the RF simulator. If you run everything on a one host, then you would have the same issues with forwarding the traffic and going through the right interfaces and so on. But you can run the core network, for example, inside of a Docker container. Maybe Navid will maybe briefly touch this later. And then you could also do this in one machine. So if you, for example, put the container, if you put the core network into some container for which there are already images, then you could also have everything that I have here in one machine. And normally I would have done this, but I recently switched the computer and I don't have the container images. I was short on time, so I just used another machine, but otherwise I would have done this too. So the short answer is yes, you can do everything in one machine.
So even the UEs and
so yes,
four parts.
Everything. What you would do, and what I have here is you have the eNode B and the UEs on one machine. So if I stop this, then you will see they both run both on Bentley, which is my machine here, Bentley. So both in my case, the core network was on some other machine, but this you could put into the container on the same computer. And then you could also do this iperf and just see iperf everything in one machine, yes.
So you do, and when you connect, for example, two machines, so we need to forward the traffic, right?
Well, that's the thing. Actually, what? Let me stop this. Kill all iperf things, and here the same. So no, you don't need to do this. So I was listening on the Bentley machine. So this is the machine that has the UE, and I was injecting the traffic on the Fumarola machine. And before you saw that there were network interfaces. I can briefly start this again. So I start the core network, HSS, and so on Fumarola. I start the base station on UE on Bentley, and I do this because what I want to show you is that there is one interface on the Fumarola machine GTP0, which is basically on the serving gateway side, so in the core network, which belongs to, and then on the other side, you see the UEs here. They all belong to the same network, because actually the serving gateway assigns the UE's IP addresses. So this is what normally happens in a network. And so on the fumarola machine, on the core network machine, I send traffic to the IP. The only interface that can go then is this one, because I sent it to this IP address and it comes out of the other machine. So in short, yes, in the end, the LTE network is a tunnel from one machine to the other.
All right, thank you.
Hello. All of this container is running on a cloud platform like OpenStack, OpenShift, maybe.
You can do this, and there are scripts, but I didn't.
You just use container directly on physical machine, right? Not in a cloud platform.
Now here, well, in this demo, I didn't even use containers. Now I was just, I mean, what you could do, and which is maybe even the easiest to start it with. So personally, I don't even work with containers or anything because I'm on the run and so on. Okay. But I directly run the programs after I compiled them. So LTE soft modem, the UE soft modem for the core network. Actually, Navid will explain this in the next session. I used the snaps. So Snap is a containerized application format. You could also have Docker containers that you could then run inside of a cloud, but on this other machine, I was using these containerized application things.
Okay, thank you.
But you could also run everything in the cloud, theoretically, yes. But for the demo, I didn't do this.
For network slicing purpose, we can use it, right? OpenAirInterface.
Yes, I will discuss this in the next section with FlexRun. I mean, I will briefly show you what you can do, let's say like this.
Okay, thank you.
Okay.
And the RF simulator, the one that shows the graphs, what kind of information can we extract from there?
Well, you could, for example, Florian, are you still here?
Yes, I'm here.
Can you answer the question? Maybe this is more founded. I can also start it again and then...
Some of the entries seem to be missing. I mean,
yeah, this is a limit. I don't know what is the problem, but this is my machine. Normally, it should look a bit differently. Sorry for that.
So yes, again?
What would you see here? Because this doesn't look properly for me. Here we were seeing the constellation diagram for push for one of the channels. Then here you see this for pure CCH. What are the other things that you would see?
So for example, log likelihood ratio. What does it mean?
Well, the log likelihood ratio is the log. So each element of this plot corresponds to 1 bit in the code word, and it's basically the after demodulation, you associate a likelihood ratio to each bit, okay, depending on the position. So if the log likelihood ratio is very high, then the bit is very likely to be 1. If the log likelihood ratio is very small, then the likelihood that the bit is 0 is very high. So that's basically the way the input to the channel decoder. So this is fed into the channel decoder such that the channel decoder can then recover potential errors in the code word.
So if there are, for example, 4 levels, because if there is 1 bit, there are 2 levels. But if there are 4 levels, then that would be higher, or it would be 4.
Well, in case of QPSK, you will only see 2 levels. In case of 16 QAM, you will see 4 levels, and in case of 64 QAM, you will see 6 levels, because the bits, depending on where they are in the constellation, they don't have the same kind of error protection. That's why you see different levels if you have different constellations.
Okay, are there more questions? So it seems not. So now it's time for a coffee break. Thank you very much, Florian and Robert, for the presentation. Let's meet again at 3:30 with the next slot.
Okay, thank you. See you later.
Okay, thank you.
Thank you.